welcome back. So today we begin with the last part of the module actuator, that is industrial servo motors, AC servo motor to be more specific. So far we have already discussed very much upon DC motors. We proceeded further and we learnt stepper motors, and then we continued with BLDC motors, whereas those kind of motors are very good for compact robot or cobotics or small kind of robots, but in industrial robots which are of heavy payload kind, they are mostly using AC servo motors because of various reasons we will discuss today. So yes, we will start today with the following outline of the lecture. These are a few. So yes, today we will begin with introducing you all to servo motors, what it is, and introduction to AC motors as such. What exactly is a servo motor? Servo motors are not always AC motors. So we'll specifically talk about AC servo motors today, and then we'll proceed with working of AC motors, a specific kind of AC motor which finds its application in industrial robots, that is synchronous AC motor. We'll discuss how it works, and we'll discuss the hardware drivers for AC servo motors, and finally I'll show you a demonstration of simple AC servo motor drive, okay, using a standard industrial servo motor drive. Okay, so here we begin today with servo motors, AC or DC. So what exactly is a servo motor? So you see, servo means feedback. Okay, so you saw your DC motor, as soon as you give it a voltage, it starts moving, right? It will start spinning. But if you want to stop it at a particular position, you have to be very specific about the kind of controller which it can use. Okay, so if you want to stop it anywhere in between at a particular angle, so you need to have something which is known as a angular position sensor. Okay, so that will give you a feedback where I am, okay, where the motor is, and then it can you can have a sort of controller which can exactly compare with the desired angle where you want, and you can stop it. So this is a type of servo which I am talking about. So this is a general layout of standard servo motor. In this figure I have shown DC motor. It can also be AC motor. It can also be a BLDC motor. This accepts some kind of signal to control its position, okay, and output is torque which it can provide, and you are loaded with some kind of load. It can be a simple link of a robot arm, okay, and then there are sensors, as I said, that can give you feedback in terms of speed. It can give you a position feedback also. So yes, position feedback can be encoded in terms of digital values, and finally it goes from here to the controller. Okay, using this position feedback, desired input is compared, and that controller gives you a kind of signal to the motor driver. Motor driver finally feeds that value to the motor. So this is your driver or power amplifier or drive amplifier, whatever you can call it. Okay, so you can also have a feedback which is torque feedback using some kind of torque sensor, joint torque sensor, and that can also be compared. So yes, using these kinds of feedback, you can have a controller which gives you a signal which can be fed to the amplifier, power amplifier, which is capable enough to do all these types of control. Not all these, you can be happy with just having a position control. So yes, this is a kind of closed loop system. Let me just draw a simple system. So you desire a position, you have a summing block here, so you have an encoder here. So this is your controller, this is your motor, and finally it gives you an output. This is your feedback sensing device. So let us say over here I am taking position, this is the actual position, and it is loaded by a kind of load. Okay. So here your load goes. Okay. So this time this is only a position controller. So error from here is fed to the controller. Controller gives kind of signal. Over here, let us say it can give you current, and finally goes to the motor, and motor runs. Okay. So this is a closed loop operation which is there, and that is what is utilized by servo motor. So yes, servo motor is nothing but any motor, not just a DC motor, with a feedback. Okay. So very much details will be covered in the module robot control, which is there at the end of this course. Okay. So this is a typical DC motor which is supporting you with all kind of prerequisite which is required to do servo control. So normally a motor runs with a very high speed. So you need to have what is known as a gearbox, a reducer, which can reduce the speed so that you can control precisely. Moreover, it also gives you a torque enhancement. Okay, if you reduce the speed, you will get higher torque. Okay, so from there it goes to the output shaft. Okay, so gear reduction is already there in place, and then this is all commutator, their brushes and all those stuffs, that is part of the motor. Now you have what is known as an encoder which can sense the angle and give you a feedback. Okay, so this is how. So you have what? You have an encoder which is here, you have a gearbox which is here, okay, and then you have a motor which is here. So overall this set completely makes it a kind of servo motor capable device. So this is a motor with some attachments. So it is not a servo until unless it is controlled by some means. Okay, so this is a typical servo motor. Okay, so now a similar one is all in one kind of unit. So you see, majority of the things are for construction of this type of compact device. Important ones are what you can see here is your PCB, which can sense the angle, and this is the gearbox which is there, and the output shaft. So and the driving mechanism definitely. So this is the coil, and you have a commutator, or it may be a brushless DC motor also. So yes, so this is what is a typical construction of a servo motor assembly. So operation wise, AC supply is directly connected to the electromagnets that creates an alternating poles. You know already by your earlier knowledge what you saw is there is a magnet, okay, in between you may have a shaft, and you have a coil that goes like this, and it is wound like this. If you flow current like this, this becomes north, this becomes south, and then you also saw you can have these kind of poles which are like this, which are at different places. Okay, so you can have a pole which is here, you can have a pole which is opposite poles which are there. So all together you have three phases, and that can create equivalent magnetic field, a magnetic field which can rotate. Okay, so yes, this is same principle which is applied here. So magnetic field generated due to the set of stator coil appear to rotate, just like BLDC motor we'll do for this also. Here we'll supply it with the pure AC signals. Okay, so advantages are it is inexpensive due to less number of parts, because there is no commutator here, there are no brushes here. Okay, and straight away you can supply the AC signal which is already in hand at your home at various places. Okay, so yes, so connectivity, it is a very convenient power supply. It is available everywhere, AC is available everywhere. So yes, that is the reason, and no commutator, no brushes, and the associated problems of arcing and wear, that is very common with a standard DC motor, but not with BLDC motor as such. It has a low power dissipation because there are no brushes, no friction, so it can dissipate less power. So there is no part which can dissipate energy in any form. Okay, only it is dissipated as heat energy due to the resistance of the coil itself. Otherwise very few dissipation is there due to the bearings only. So motor inertia, rotor inertia, if it is designed in such a way that it is low, so those kind of rotors are very responsive. you apply a current, you generate a field, immediately your rotor can follow the rotating magnetic field. They are very, very responsive. If it is a bulky and heavy rotor, in that case it will be little dumb kind of, okay, so it won't respond so quickly, okay. So that is the reason it is made very light. It is highly reliable, robust, easy to do maintenance, you know, and it definitely for these reasons it has longer life also. Okay, so now let us just look at quick disadvantages of AC motors. They have little less starting torque, so it finds some difficulty in starting. Otherwise, if it is running, you can continuously keep it running. Okay, so starting wise, it needs to have some kind of auxiliary device to start the motor. Sometimes you have a coil which is something like induction motor, so it starts like an induction motor, your fan, and then it becomes a synchronous motor or any kind of AC motor. There are some devices also, star delta kind of starter systems are there. There are many other similar approaches to it. So it needs auxiliary device to start the motor. Difficulty of variable speed control, because you know you have fixed frequency at home, it is very, very difficult to change the speed of such kind of motor. You must be thinking we are easily controlling the rotation RPM speed of our fan. Yes, we are doing so. We are wasting a kind of energy, sometimes in resistance, sometimes in capacitance, and sometimes we are losing upon the torque while doing so, right. So that is what we cannot sacrifice when it comes to driving industrial servo drives, where torque is very much a prime thing. Okay, so yes, you have to maintain the speed without losing much of on your torque. So yes, you have a kind of thing which is known as a servo control. We will discuss on this now. The use of modern solid state and variable frequency drive, here is the term for that modern thing. Yes, variable frequency drive with field feedback compensation makes it a complex system, but yes, without this there is not much of an alternative to. So we should be happy with it that nowadays with modern electronic systems this has become a quick possibility, and it is quite inexpensive nowadays. Okay, so yes, there is definitely some shock hazard. You have to be little careful. Rest is fine. Okay, and note due to its simplicity, ease of use and low cost, it is widely used in all modern industrial robots of different capacities, because it can provide you with huge amount of power, okay, which is not possible with small DC motors or sometimes even BLDC motors. So that is the reason we have to stick with AC motors if we talk about big robots, okay, that are there in the industry. So let us just discuss the working principle of synchronous AC motor. So yes, as I have told, you have a 3-phase stator winding carrying 3 phase of currents that produces 3-phase rotating magnetic flux and therefore rotating magnetic field. So yes, just now I have shown you, you have multiple poles which are there. So you have poles here, you have poles here. So you have another pole here and pole here, you have yet another pole here and pole here. So each one of them can be north, south, okay, if one is north, other one is south. So this can create a field which is which can rotate, okay. So this field can rotate. So alternatively you can shift the pole from here to here, okay, you can shift the pole from here to here and your armature keeps on following the rotating magnetic field. So this is the principle which remains here also. So rotor is provided with a DC supply. So your rotor is provided with a DC supply, that is a kind of magnet which doesn't change its polarity, or it can be just a permanent magnet. It can just be a permanent magnet which locks in with the rotating magnetic field and rotates synchronously along with the rotating magnetic field. Once the motor is in operation, the speed of the motor is dependent only on the supply frequency. So rotating magnetic field is because of a fixed frequency supply, okay. So the rotating magnetic field rotates with the kind of frequency of the inputs AC supply which is there. So in order to change the speed, you have to change the frequency. Okay, so that is, there are few disadvantages to this also. Okay, so this, because of its compact nature, heat dissipation is a problem. So yes, with smart designs nowadays, it is now a possibility to design it very small, but yes, that heating is a problem. So you need to have good arrangement to dissipate that kind of heat which is generated while it is running. So synchronous motors have a high rotor inertia because you know it has magnets. Now you know it has permanent magnet or maybe some exciter coil, so that makes it very heavy. So that is the reason it doesn't pick up speed immediately on applying a rotating magnetic field. Okay, so they don't have some self-starting kind of thing. So squirrel cage winding, induction motor kind of winding is there to self-support this kind of starting problem. Okay, so yes, that is there, and you see quickly now. So this is the three-phase I am talking about. So now again star connected we discussed very much in detail while we were discussing BLDC motor. So you see here also. Okay, let me just vanish myself from here. So yes, so this is there. So one of them, let us say if it has V is equal to V0 sine omega t, other one will be, next one will have a voltage which is something like V is equal to V0 sine omega t plus 120 degree. The third one will have a value which is something like this, V is equal to V0 sine omega t plus 240 degree. Got it? So yes, it should be something like this, so that all the phases are there. All the phases are part of three-phase AC supply. So this creates a rotating magnetic field here. Got it? So you see now if one of them has this one supply, two supply and third one, so 1, 2 and 3, so this will create a field which is rotating in nature. Okay, and that carries a rotating magnetic field. So everything depends on the kind of frequency which is supplied from here, the frequency which is supplied here. So this is the frequency. So okay, so with this frequency the field will rotate. So this carries the armature along with it. So now the rotor, which is also the armature, has got the permanent magnet that follows the magnetic field. So this is how it works. Okay, so now let us move ahead. So how to do that? How to do that? You cannot create a variable frequency out of because you know now you have to have a rotating magnetic field with a different speed. So speed of that rotating magnetic field is dependent on the frequency which is supplied from the AC supply. Okay, so yes, so in order to control omega, it is very difficult to use standard AC supply, three-phase AC supply and do that. So what we do, it is we first do this. So yes, you are supplied with three-phase AC, so that goes here. This is a three-phase rectifier and a filter. Finally you get, so after three-phase rectification you get a supply which is something like this. So once you filter it, you get a DC. Got it? So ultimately you have converted a three-phase signal to a DC signal. Okay, straight to this is the voltage, this is time, so it remains constant. So that is a DC supply. So with this DC supply, now you have a three-phase inverter over here. What it does basically, again if you remember, we have talked about this kind of switches. Okay, you have talked about this kind of switches where you have two switch A and A bar. So that used to switch the polarity which is here. Okay, polarity which is here. So similar is the thing which is here for three phase, again just like a BLDC motor driver. Okay, so what it does, it can gradually switch its polarity from, switch the pole from here to here. Okay, from here to here. So in order to do that, each one of them is supplied with a kind of PWM signal, pulse width modulated signal, which is nothing but a variable duty cycle square wave signal. So you see the density varies like a sine wave. So equivalent voltage that goes here and here is controlled. Okay, so equivalent voltage that goes here and here is controlled. So what is happening here? So you see a sinusoidal signal kind of current you can get. Okay, so this wire gets a signal which is something like this. Okay, so effectively now this one, the second one over here and here will see a signal which is phase shifted by 120 degrees. Okay, and that also will be something, it will start from here, it will go like this and follow something like this. Okay, so yes, this is 90 degrees, somewhere 120 degree and 180 degree. So yes, it starts from here, it follows a phase shifted one, and this is a different waveform which is V is equal to V0 sin omega t plus 120 degree. Now the third one is triggered here and here, and there is yet another waveform that is starting somewhere over here and that goes like this again. Okay, so that is V is equal to V0 sin omega t plus 240 degree, not exactly 360 degree. So 240 degree it starts. So this is 270, so it is in between this. So yes, so this wire will see a signal which is phase shifted by 240 degrees. So this is actually creating a three-phase signal over here, Now we started with a three-phase, we are ending with a three-phase. So what is the beauty over here is you have full control over this signal, that is input to this PWM inverter. So this inverter now can generate frequency of our requirement. So this AC which is coming here, the AC which is fed to this motor ultimately is controlled. Okay, so the input frequency cannot be controlled, but the output one is in our control. So your PMSM, that is permanent magnet synchronous motor, now is fed with the AC, three-phase AC, for which your frequency is under control, and you can have variable speed rotating magnetic field, and you can control the speed of your motor. Got it? Okay. So now synchronous AC motor also has got some advantages. We'll see it here. So especially useful in applications that require precise speed, the kind of robotic arm, they require precise speed or position control most of the time. Okay, so speed is independent of the load. You see, if you increase the load, your speed is not going to vary. If you have pre-calculated it well, you know how much torque which is going to come, it is not going to slip over torque. In that case, it will simply follow the speed at which you are supplying the frequency of the AC supply that is fed out of your variable frequency drive. So your rotor will rotate at the exactly with the frequency which is desired by the variable frequency drive. Okay, so yes, it is independent of the load. Now speed and position may be accurately controlled using open loop control. Yes, so if you stop it somewhere in between, so if your three-phase, let us say you had a three-phase that had some kind of voltage and I stopped somewhere in between, each one of them is halted. Okay, so all the poles which were oppositely placed have a particular value and it remains there. So your field stops rotating, but that is a field, your magnet will get stuck there. Okay, your magnet, that is the rotor, will stop there. So that is the holding torque that it will get. Okay, so you can stop your omega anywhere, and omega can become equal to 0. In that case, your field doesn't rotate, it remains where it is, and your armature also remains there. Okay, so it can stop also, or it can reverse its direction also. Got it? So yes, omega can be positive, omega can be negative also. So low power application includes positioning machines where high precision is required, such as robot actuators. It can hold its position. When a DC is applied to both the stator and rotor winding, it is just like a DC. If voltage is not varying, it is remaining there, it is just like a DC. So you can make omega is equal to 0 omega everywhere. So you just remember V is equal to V0 sine omega t plus phi. This is the signal which is going to the different coils. So this is what is the omega I am talking about. Okay. So this omega can also be equal to 0. In that case, voltage becomes constant. You see, this is a constant for a particular coil. So yes, it is programmable. This VFD has some controller in between which can take up the signal, which can feed the desired signals to the coils. Okay, so the VFD has got some input device that actually controls the omega, rotating magnetic field which it is able to generate. So that omega can be controlled directly using that. Okay. So yes, that is used definitely for turntable CNC robotics assembly lines. So it has very good efficiency in low speed applications also. It doesn't find its application just in high powered industrial robots. It has many other automation application it is used. Okay, so the type of drive as we have discussed now is known as variable frequency drive. Okay, it is of various types. It can be a voltage controlled, voltage source inverter, or it can also be a current. So you can have a current which is like this. If you want to control the torque, you have to use current based. Otherwise, for speed control, voltage one is quite commonly used. So that is commonly used in robotics, both the kinds. Okay. So controller type can be a PWM, scalar control. All these kinds are taught very much in electrical engineering. We will just get the names of it at least here, so that you can have some analogy with your understanding here. So yes, PWM scalar control is there, the one which you saw here. Use some kind of PWM signal, that is a scalar field oriented control, that is a vector control. So yes, those kind of, or direct torque control is there. These are some major types. There are many other types of controller which is there, which can control this kind of motor. Okay. So yes, so this is the complete picture of a typical permanent magnet synchronous motor control system. Okay, so you see it has everything here. So this is a torque controller. This is a torque controller which ultimately feeds current to this motor. Okay, so this may be a current controlled drive. So yes, so current is fed here to this permanent magnet synchronous motor actuator, and finally you are getting some kind of torque here which is now connected to a load maybe. Okay, so that is connected with a load, and you are sensing what? You are sensing the angle position, and position is fed back here, It is compared with the desired angle and actual angle. So you take difference of that is the error. You have a position controller over here, maybe a PID controller most of the time. We will discuss about PID controller in last part of this course also. Okay, so this is your finally kind of signal, a velocity signal which it is feeding. So yes, it is relating the error to the velocity which is desired, which should go to the motor if it is connected directly. Okay, so yes, now you have actual angle which is going here, and you are calculating maybe a differentiator circuit which is here, which is able to calculate omega, that is the angular velocity of the shaft. This is the actual omega which is fed back over here. So this is the actual omega, this is the desired omega. So actual omega and desired omega, you take the difference. So difference between those two omegas, angular velocity is now fed to the speed controller. So speed controller gives you an output in terms of torque. It gives you an output in terms of torque. Okay. So now there is an interesting part over here. So you see difference in the angle, you are feeding angular difference, and you have a controller which gives you a desired omega, that is the angular velocity. Now you are sensing you may have a direct angular feedback over here, or you may just have a velocity sensor which is taking the omega. So you don't need to convert angle to the velocity, rate of change of angle. Using rate of change of angle, you can directly get the velocity feedback, and you can compare over here in this controller in summing block. And finally the difference is going to a speed controller, that is output gives you an output of torque. Now you need what? This is the desired torque. This is the desired torque. So how much is the actual torque? So in order to get that, you have a model of your system most of the time. Okay, you have a model that actually calculates how much is the model of the motor maybe, or model of the system which is all attached with this actuator. Okay, so that model gives you, by measuring the current in its coil, it is able to estimate the actual torque. It is able to estimate the actual torque. So this is the desired torque, this is the actual torque. Difference is used by this torque controller. Ultimately it gives you an output which is current. So current is finally fed to this. So it is a 3 independent controller which is going one by one. So inside one is the torque, next upper one is the speed, next upper one is the position. So you are able to control the torque, you are able to control the speed, you are able to control the position. Okay. So yes, you can have somewhere in between, see this is desired, you can have some desired input velocity fed in between over here. Instead of this calculating the desired signal, you can have directly velocity feed from here. You have to just discard the outer loop which is before to that. Similarly, you can have torque feedback, desired torque which goes here. You just have to ignore rest of the upper loops. Okay, so direct torque control is possible. Okay, so this is a permanent magnet synchronous motor control scheme which is there, and this is normally embedded inside your standard AC servo motor driver. Okay, so yes, synchronous speed, if you have a background of some electrical engineering, should be quite good enough. So it tells you synchronous speed is equal to 120 F by P. For those who are not from electrical engineering, this is a ready-made formula for you which gives you relation between the synchronous speed depending on number of poles you have. Okay, it is not just 3 pairs of poles, there are P number of poles which is here. So in that case, the frequency of AC supply gets further divided by this. Okay, so your ultimately synchronous speed is equal to 120 F by P. 120 F by P. F is the frequency of AC supply, P is the number of poles. So ultimately this is the speed with which your magnetic field will rotate. Okay, so slip, if at all it is having a load which is more than desired, so there is a term which is known as a slip rate in synchronous motor. This is a undesirable thing in case of robotics. You should not slip anywhere. Okay, so yes, so this is your slip, error in the rotating magnetic field, whereas actual rotor speed is something different. So difference goes here, and denominator you have the synchronous speed. So it is sometimes expressed as percentage. In that case, you just have to multiply this by 100. That's all. Okay, so this is your standard servo motor controller. Okay, so yes, this is one of such controller which takes care of everything. It can directly take in input and through E-bus system. So this is your E-bus system with which you can feed in the signal. This is connected in a bus fashion you have seen earlier. Yes, so this can run using 24 volt DC signal. Maximum current that it can take up is 4.5 ampere RMS signal that goes to the power contact. Power contacts are here. So peak current, at least for 1 second, it can handle up to 9 ampere. So you should be very careful. If your robot collides somewhere, it should not remain in that position without getting switched off automatically. Okay, so you should not go beyond 1 second with this much of current. Okay, so yes, supply voltage can be anywhere from 0 to 48 volt. that is an external supply, that is for the motor, whereas 24 volt which goes here, it is not for the motor, it is for the control system. Okay. So brake current is something like this. So your motor may be having a kind of brake shoe which holds your rotating shaft. Okay, so that also uses electromagnets to energize that. So that is that can draw some kind of 0.5 ampere for this type of motor. Okay, so this is there at least in this motor. So yes, PWM clock frequency is 16 kilohertz, and you see there is a current control frequency. So now the controller you saw earlier, now you look at very carefully. So there are different frequencies for each loop. So this controller works with a different frequency, this one with a different frequency, this one with a different frequency, and you see here, so highest frequency with which it is working is the current control loop. Okay, and then you have a speed control frequency is something around 16 kilohertz. So speed control is 16 kilohertz, current control is 32 kilohertz. Okay, and as an input it can have end position so that it can stop at the extremes. It can have one feedback from the encoder or maybe a resolver. It can have different other kinds of angular feedback, so that can be taken up by this kind of servo drive. The one which I use, this one, is can take feedback which is very much like an optical encoder. So yes, that goes here. So output is nothing, it is servo motor output, that is UVW, 3-phase output. So one doesn't mean just one wire, it has 3 wires. Similarly for brake it has 2 wires. Okay, so that goes here, that is to apply the brakes. Okay, and it is all this is in one cable technology which is specific to Beckhoff. Other motors may not have such. The one which I have it here today, you just see it carefully. So yes, I'll just make myself little bigger now. So you see this one. So how does it look like? It has 2 wires. Okay, so first side, you see what all parts does it have. This is this part is the motor. Okay, this part is the motor. This is the shaft which can rotate. So I can feel the thuk thuk thuk, those kind of stops there, because it is permanent magnet which is mounted on top of this rotor. So yes, it is there, and this cage must be having poles which create some rotating magnetic field which is followed by this one. So what is the at the end? At the end, this section is nothing but an encoder. So you have 2 separate wires. So one is for, you see this one is for encoder wire. So this is having, I can see plus VCC, ground, and 3 signals. So it may be a kind of resolver which gives you an output in 3 different wires. Okay, so yes, and then this is 3-phase and 1 ground, 4 wires. This goes to the motor part of it. Okay, so yes, this is how it looks like. This is a Panasonic one. There are many other makes which are making this kind of actuator. So let us go back to my normal form. Okay, so I am back. So yes, so this is your thing. And then isolation, definitely it is an industrial motor, so isolation is something around 500 volt IP20 class, ingress protection, and relative humidity. Non-condensing is something around 95% it can handle, and communication it uses E-bus. Okay, so that takes up, that can change the all runtime variable that is accessible to the twin cat system that I commonly use to demonstrate all these I have shown so far. Okay, so yes, this is the motor which I am going to use today. So this is a standard servo motor, AC servo motor, similar to the kind that I have shown, but yes, it has just one cable technology. So your encoder wire and your power cable both goes from a single bonded cable. Okay, so doesn't matter even if it is separate. So this is permanent magnet excited 3-phase 4.7 ampere. When it is standstill, rated speed is 4500 RPM. So it requires a gearbox if you have to control that is to enhance the torque also. and to reduce the speed. So you see maximum torque which it can provide is, the peak one is 1.36 Newton meter, whereas it is rated with 0.38 Newton meter only. So this much is not sufficient to drive industrial robots. So you need to have some kind, let's say if you have something around 100 times gear reduction, so this is approximately going to give you 38 Newton meter of torque. So yes, this is sufficient to drive a industrial arms, industrial robot arms. So yes, this is sufficient for at least last 3 links. Okay, so this is there. So your gearbox will enhance the torque, at the same time it will reduce the speed. So yes, and then rated power is this for this one specifically, and nominal voltage is something around 48 volt that I will be supplying. Multi-turn feedback, it has a feedback of something around 18 bit of feedback. So whatever is the type of encoder which is here, that is now encoded in a bit fashion, digital way, to 18 bit of signal. So yes, you understand now how precisely it can give you the feedback. Okay, so rotor moment of inertia, it will be later used to create a controller model for it. So this is the rotor inertia. Lighter is better. Now you know they are more responsive. Flange size is 40 mm. Depending on your application, you have to select one of them. Protection is IP54. Again, I am going to use TwinCat 3 configuration that I made similar to the DC motor or BLDC motor or stepper motor. We will do similar sort of arrangement here also. And I will be using TwinCat ADS library that I will be importing to the Python environment to access the runtime variable, speed and position. Okay, so let's go to the working demonstration of this. So before to that, let me just show you the circuit once again. It is exactly the same, apart from this driver which is here. Everything else is same. So this is your IPC industrial PC, this is your HMI, this is PC, industrial PC, this is UPS, this is your power supply, okay, 24 volt, 120 watt. This is EtherCAT coupler, so that can take in signal from here. Okay, so all the data comes from here and later on communicated from here to bus system. So from these buses, it is transmitted to other devices. Okay, ultimately it reaches to your motor driver. Okay, so now these are the connections which you can make. So this is basically for the feedback. You see, feedback, 2 feedbacks, that means it must be some optical encoder. Okay, and motor phase UVW, 3-phase wire is there, and then there is a connection for brake also. But the motor which I have used, AM8112, doesn't have the brake, so these were not connected. Okay, others were connected. So even without brake, you know, if you stop rotating your magnetic field, your field remains in its place with a given power and your rotor can be halted anywhere it is, okay, while rotating. So even without brake, you can have some kind of holding torque. If that is not sufficient for the safety reason, when the power goes off, in that case you have to apply physical brakes. Okay, so this is the arrangement. And finally, let me run this servo motor demonstration video here. You see what I am trying to do here. So I am continuously feeding it with a given value, that is A, to control its step and some angle. So it will gradually go there. Okay, and I will come back again. So it went till 180 degree and it came back. That is the position control I was doing. Again, I am coming back and remaining there first of all, and then I will go to some other angle again with some different velocity. This time it is 360 degree. Okay, it precisely obtains that. You can closely look at these codes that I will be sharing. Okay, I will be sharing all these codes, all the resources, this TwinCat code as well as the data sheet of these motors, the drivers, everything will be shared as a resource for this lecture. not just this lecture, any other lectures also. Okay, so with that I would end here, at least for servo motor. Let me just talk about the kind of selection of these kind of motors, how you can do selection. So at least for AC servo motor. So let us just switch to this window. So this is one of the product which is made by Kollmorgen brand. Okay, so this is a kind of motor it can make. This is servo motor. Okay, this is the motor which you want, and these are the drives which it is making. Okay, different other accessories are also there, but forget about that. At least motor and the drives on which you are interested in. So there are many other systems which are integrating the drives, multiple drives together in a single one, like this one. So there are many of these kinds which in a compact way it is integrating 6 axes to say, and those 6 axes accepts different kind of robot architecture. Okay, it can be a CNC machine, it can be a Delta robot, it can be a 6-DoF steward platform, it can be a standard serial robot or any robot. The kinematics are linked by different servos. So all the kinematics can be fed in here, so that you just give the end effector position. This calculates, this motion system will calculate the motor angles and finally feed it to the 6 motors which are connected to this, 6 or 3 or whatever. Okay, so this type of motion systems are also there which can import kind of kinematics directly within this motion system. Okay, so advanced drives are also there. So this is just a drive, individual, you have to take care of kinematics and the relation. This is just a motor. So Kollmorgen is one company, there are many other companies. This is Beckhoff. So you see it makes different kinds of servo motors and its drives also. Okay, so yes, depending on your rating, your current, so I'll talk about that very much in detail after this. So yes, this is another one, yet another one. So this is a company which is in India also. So this also makes AC and DC, brushless DC servo motors and drives also. So you have Sigma. This is Yaskawa. This is Yaskawa. You see, Yaskawa also makes motors, their drives. This is Panasonic, the one which I had just now. ABB is also making it. You have Moog Controls, they also make. You have Keyence, that is a Japanese company. Panasonic is also Japanese. So there are many makers you will find. So what all parameters before you select one of them you have to look for is sometimes even product configuration greater which is there with Siemens. This makes things very much simple, but yes, once you look at the product specification sheet, the one which I showed you just now for the controller and for the robot, for the motor, so you can quickly compare that with your requirement and you can select a motor, whereas what is available with a particular kind of manufacturer, you can have a selection sheet like this. This lets you selecting the converting system, okay, voltage level, what is the voltage level you want, shaft and side, okay, shaft and side, what kind of version you want, it can, so flange or it can be angular flange, okay, so what should be the height, what type of cooling, how much is the static torque that you are looking for, maximum speed, holding brake or not, dimensional thing, everything is here. You see, encoder system, if you want, what sort of encoder you want, okay, so incremental or absolute, okay, so resolution, how much resolution do you want, okay, and kind of encoder, different kind of encoders can be selected which can be mounted. Type of gearbox is also here, okay, different types of gearbox it allows you. These are the ones which are made by Siemens, but you can always have, because these motors are designed with NEMA standards, so you can have any other make gearbox also for this reason, okay. So you just have to take care of the maximum torque that it can handle, otherwise it is all the same. Gear ratio is to be fed to the, is to be put to the configuration of your system, so that you get better understanding how much torque is getting multiplied or how much speed is getting reduced. Okay, so explosion protection if you want it, so that also is achievable. So for painting robot or those kind of things, paint finish and many manufacturer specific options are there. So these are few parameters which you should look for while selecting this kind of motors. Okay, so this is specific to Siemens, but there are other makes also which are there. Okay, I'll just end here AC servo motors. We have learnt a lot about actuators. That should be sufficient at least to begin with designing your robot. Maybe at least you can now understand how my robot is working, industrial robot is working. So what all things that goes into control of those kind of actuators, you know, right? So what additional reading I have suggested here is data sheets. You should start looking for the data sheet. If at all you see your robot, you just look at the motor model and try to browse through that kind of data sheet, try to get hold of those data sheet and see what is the specification of that, what is the gearbox which is mounted, NEMA flange standards, okay, different kind of standard is there, so which one is fitted here, okay, IP certification, okay, is this enclosure safe for the kind of application I am looking for, ISO standards, what is being followed by this type of actuators, gearboxes, encoders, resolvers. We'll talk about this in next module, that is sensor. So that is a kind of feedback, angular feedback these motors were giving us to do proper control. So yes, in next module we'll be discussing about sensors. With that, thanks a lot for covering this module. We'll see you in next class. That's all. Thank you.